Assalamu alaikum. Today we are going to talk about module 2. We are in week number 4 and our topic will be the data path. The course learning outcome covered by this module, we identify the main units and instruction set of the computer architecture. So in week number 4 we are going to talk about the data path. Week number 5 we are going to talk about single and multiple cycle computers, and week number 6 we are going to talk about the instruction set architecture. So what is an ISA? An ISA is the specifications of a computer that appears at the lowest level for a programmer, or basically it's the building blocks of a program. The computer architecture is the high level description of the hardware implementation to drive the ISA. So as we said earlier, the first step is to build your architecture. The first step is building our instruction set architecture. The second step, we build the hardware that supports this architecture. Then we start writing our programs. So the architecture usually includes specifications such as speed, cost, and reliability. So the simple computer architecture is composed of a data path for performing the operations and a control unit for controlling the data path. So previously, if I ask you what is a CPU built of, you are going to tell me three things. Usually you tell me a set of registers, an ALU, arithmetic and logic unit, and a control unit. So now the set of registers and the ALU are constituting our data path, whereas the control unit controls this data path. So the data path itself is basically the set of registers and the micro operations performed to store data into these registers, and a control, of course, interface in order to communicate with the control unit. So the guiding principles of building data paths are basically the set of registers and the implementation of micro operations. The set of registers, we call them a register file. We will always refer to the registers as a register file. These are a collection of individual registers. The micro operation implementations are basically one or more shared resources for implementing micro operation. We need also the buses, and we need the buses and the arithmetic and logic unit. And the arithmetic and logic unit, we will furthermore talk about it and say it's called now the function unit, because it's not only arithmetic and logic, we are going to call it the function unit. Now, if you look at this first data path, this is our first data path. Let me just change the colors here. You can see we have 4 registers. You can see that we have 4 registers, R0, R1, R2, and R3. These registers are all connected to 2 multiplexers, which is select A and select B, as you can see. And this blue box over here is called our register file. So our register file consists of 4 registers, 2 multiplexers, a load enable circuit with a decoder. Now the output of this register file is either data A or data B. Data A, as you can see, it immediately goes to our function unit. Okay, it immediately goes to our function unit. Our data B, on the other hand, goes first to a multiplexer, which selects between either bus B or a constant n. Then it goes to either the arithmetic and logic unit or to the shifter circuit. So whenever we have a shifter circuit, it's going through bus B. Now the arithmetic and logic unit has 4 selector lines, which are called G select, and it has VC NZ outputs, which are the status bits, overflow, carry, negative, and 0 bits, which are the flag register. The output goes to a multiplexer once more, which is F multiplexer, and it selects by either taking the arithmetic and logic output or the shifter. Their output will go again to MUX-D, which also selects between 0 and 1, where 0 is from the function unit, 1 is from data N, and then our output from MUX-D will go to the register file over here, and it will be connected to either R0, R1, R2, or R3. The selection of these depends basically on the load enable over here, which is the decoder 0, 1, 2, and 3. The destination select is from the control unit. All of the control signals are coming from the control units signals are coming from the control unit. So the control signals we are talking about over here, I can show you. We start with select A, select B, MB, constant N. Then we have G select, H select for the shifter, MF select, MD select. We have destination select, load enable. All of these are signals coming from the control unit. So let's say that we want to sum two signals which are, um, R2 plus R1, put the result into R0. R2 plus R1, put the result into R0. So first of all, we are going to apply 0, 1 to select A. 0, 1 to select A means we are going to select R1. Okay? Remember, it's a multiplexer. Once you put 0, 1, you are going to select R1. And we are going to put 1, 0 into select B. So we are going to, in select B, we are going to put 1, 0, which is going to give us R2. So R1, you can see here the line, R1 is going through bus A, and R2 is going through bus B. Then we are going to select MF equal to 0 in order to have the input coming from bus B going into the function unit. Then we need the G select value, which will be 0, 0, 1, 0. So this means that we are telling the arithmetic and logic unit to apply an addition function. MF will be set to 0 in order to select the arithmetic and logic unit, and MD will be selected to 0 in order to select the input coming from the function unit. Then in the destination select, we are going to put the result in R0. So the decoder will be having a value of 0, 0 in the decoder, and load enable will be equal to 1 in order to load the value and store the result into R0. So this is the basic operation when it comes to the data path. Okay, once more you can see here that this is our data path and the instructions. If I say R1 plus R2, put the result into R0, where do we start from? We always start from the registers R1 and R2. So I need to select them. So R1 will be selected by 0, 1, and R2 will be selected by 1, 0. Then we start going with the flow of the signal. This is R1 going here. Now when it comes to R2, we need to go to max B, so we put max B to 0 in order to let the signal pass here. We put 0, 0, 1, 0 on the G select in order to select the addition. Then we put 0 here in order to take the value from the ALU, 0 to take the value from the function unit, and 0, 0 to select R0. Load enable should be 1. Now, the key controls are MF, which is used to select the arithmetic and logic unit, MB, which is used to select whether I'm taking an input from bus B or from a constant N, MB is used for bus B or constant N. MD is used for function unit or data input. And the decoder is used to set our destination value. Now, before continuing, let's start talking a little bit about our arithmetic and logic unit, the ALU. Our ALU will be doing the arithmetic and logic components. So we talked about this in COMP4113 in level 2, and we designed an ALU. So here it's more or less the same. So the ALU needs to do the arithmetic circuit and a logic circuit, then a circuit which will choose between the arithmetic and logic circuit. So the arithmetic part is consisted of an n-bit parallel adder, and the logic part is basically logic gates with a multiplexer. We are going to talk about this over here. Now consider this circuit. This is your 4-bit adders. So this is X, this is Y, and we are basically doing X plus Y plus Cn. We are basically doing X plus Y plus basically Cn. Now X is quite simple, straightforward. Depends on what we put over here. Depends what we put over here. Now look, if Cn is equal to 0, it will give us an output, and if Cn is equal to 1, it will give us an output. Now, if what is coming here, which is B, is equal to 0, so if here I have G is equal to X plus 0 plus 0, because Cn is equal to 0, then G is equal to A. If the input here is equal to B, then A plus B. If the input is equal to B complement, sorry, this is B complement. If the input is equal to B complement, then this is A plus B complement. If the input is equal to 1, then it is A plus 1. Then it is A plus 1. Now, if Cn is equal to 1, the first one will be A plus 1, then A plus B plus 1, then A plus B complement plus 1, then A plus 1 minus 1, which is equal to A. Then A plus 1 minus 1, which is equal to A. Sorry, this one is right. This one is minus 1. I will be explaining this later on. Now, the functions over here are basically a transfer function, an add function, a decrement function, an increment function, a subtract function, and a transfer function. These two have no meaning, so we are not going to include them. How is this a subtract? This is the 2's complement subtraction. Okay, 2's complement subtraction. This is a decrement, transfer, increment. These are the useful functions that we can produce. As for the logic circuit, you can see it's quite simple. We have an AND, an OR, an XOR, a NOT. Put them all together through a multiplexer and combine them. You get your basically an ALU, which will look something like this. So this is our ALU circuit. Now, in the next part of this week, we are going to talk about the combinational shifter parameters and how we build a shifter circuit. Thank you for watching.